just want to say thank you everyone for coming. This is probably the largest meetup this Chicago Haskell group has ever had. So you guys are witnessing history, and we're glad you're participating with us in this historic event. I have the privilege of introducing our speaker today. He is a co-organizer of Chicago Haskell. He's also the director of engineering at Helium.co. It's a startup based out of San Francisco, catering to the Internet of Things industry. And I'll just let Reid take it away. So.
Yeah, thank you. Thanks for having me today. Thanks to Pivotal for hosting and getting food, and everyone else for organizing and coming. This is going to be pretty casual, so feel free to interrupt me with questions. I'm sure there'll be some discussion afterward. So today I'm going to be talking about how we're using Haskell in production. Specifically, this is like what we're doing today, not what we wish we did. There's a lot of things that we wish we did, right? So everything here is sort of a snapshot in time. Other people might be running Haskell in production differently, and that's totally valid. So this is by no means meant to be like the way that you run Haskell stuff in production. Basically, what I want to show is that running Haskell in production is actually pretty easy. It's not that much different than running a Java or a Ruby app. So if you're not running Haskell in production and you're kind of worried about that part, you're like, oh, writing type-safe Haskell code is really cool, but how do I convince my team to run it in production? Have we figured out things like the build server, deploying, monitoring, all that kind of fun stuff you have to do? Hopefully this will kind of give you some insight to that stuff not really being a mystery. So this is at the company I work for called Helium. We make products for people typically who are developers working at companies that want to make products and services in the Internet of Things. So we have a little sensor that is battery powered, communicates with the network over the radio, and you can actually put Lua code on it and read temperature, send it to our server once every 10 minutes, have that last for a couple of years, and then using an HTTP API, receive everything that you send from these sensors on the other side and do interesting things with that data. So we've been using Haskell in production for a little over a year now. So this is kind of the culmination of how that's sort of come together. I'll start with kind of just some anecdotal things. Typically in Haskell we like to sort of speak objectively and stuff, but I think it's important to kind of talk about some of the softer side here too. So of the projects I've worked on, this has had the lowest defect rate for the same level of effort of any software project I've worked on in my career. And that's cool for a couple of reasons. It's good for the business, obviously. You want to make a product that you're proud of, that your customers can actually rely on, but it's also a lot more fun to work on new things rather than constantly kind of fixing the broken shit that's in production. It's also been the easiest to refactor. I think this is probably like the Haskell secret that people who have used Haskell in production for a little while kind of discover, but is actually not talked about that much. Typically, people think of Haskell as like this kind of, ivory tower language where you like lock yourself in a room and figure out like the perfect solution to something and then you never change it. That's actually really far from the truth, or at least it doesn't have to be the truth. You can come up with something that's actually just like the minimum thing that can solve your problem, and then trust that you'll be able to refactor and change it as you understand the problem better and as your business needs change. So of all the kind of things I've enjoyed about Haskell the most, this has been the most fun. I can just make like 1,000-line change to our product in a few hours and feel really confident that it's not going to touch some other part of it that I didn't intend to be changing. It's been the most enjoyable. Being able to actually change things and focus on what's new makes work more fun. It's not as fun to go kind of fix some broken part of your software that has nothing to do with what you intended to work on. And typically speaking, we've found relatively well-documented libraries for pretty much everything we've had to do. We have a few of our own open source libraries that I'll talk a little bit about as well. But for doing sort of typical back-end web type things, there's an open source library for pretty much everything you're going to want to do. There's a bunch of web server choices, web frameworks, HTML, CSS generation, talking to databases and stuff. So the state, now in 2016 is a lot different than it was in, say, 2010 or so. A lot of these things that you're typically going to be doing in, a web application have pretty mature libraries for. So the context I'm going to be talking about this in is our project, which is about 20,000 lines of Haskell now. There's 5 or so of us who kind of work on it full time. We've actually been ramping up quite a few more people who are doing some Haskell EDSL stuff on our embedded side. But this is sort of just the platform backend code side. And we've got about 6 different services in production. So we're going to kind of look at how we build code, how we deploy it, monitor it, test, and then we'll look a little bit at how Haskell makes actually developing some of these things, I think, better and really kind of shows off the type system. So first talking about building, how many of you have heard of Cabal Hell before? Yeah, so if you've used Haskell before like the middle of last year, you've probably experienced Cabal Hell, and I feel comfortable in saying, at least for me, it is completely banished. We've moved over to a tool called Stack now, which I think has just been awesome for us. It has solved pretty much all of the problems that we had with Cabal, and it's pretty quickly went from Cabal and the Haskell build infrastructure being kind of one of the worst build systems for, reasonably popular languages to one of the better ones. We switched our whole product over to Stack in the course of like 3 days and haven't looked back since. So if you're at all considering working on a new Haskell thing, I highly recommend just going straight to Stack and completely ignoring Cabal. There's obviously cases where Stack can't do everything, but for the most part, use Stack instead. So this is just a simple example of how easy it is to get started with Stack. So this is a project that was using Cabal before. When you type Stack in it, it actually looks at your project and gives you sane defaults based on your Cabal file. So that's what it's doing in this first step right here. And then we're going to build the project. And that's pretty much it. And what's cool about Stack is that it also cuts down a lot on your compilation time. So typically with Cabal, you had a sandbox where all of your dependencies would go in there. And if you pull in like just a single thing that has a lot of transient dependencies, like lens or something, your compile times are going to be like 20 minutes from a from-scratch installation where you have no dependencies. And because of some of the wonkiness of Cabal, you typically wanted to do that to make sure that your project built from scratch as opposed to built with like some set of dependencies that were already there that you can't really reproduce. So Stack mostly solves this problem by having 2 immutable snapshots and then a project-specific one that can actually be mutated. So there's the GHC packages, which is just things like base, GHC prim, stuff like that. Those are going to be GHC version specific. Then there's a specific stackage snapshot, which is versioned. So I think they just came out with version 5 right now. And that's basically like a collection of 1,000 or so Haskell libraries that all compile together. They all have their test suites pass at that specific version. And you just depend on that one thing, and you get all of these packages in the ecosystem that are, for the most part, the kind of things that you want to be depending on. And that gets shared across all of the projects on your machine. So if I have 10 different little Haskell projects that all use Stackage version 5, they share all of that base set of dependencies, and I only have to rebuild that set once. And every time I upgrade to a new snapshot. Then you have your project-specific packages. This is a mutable database. Here you can either have projects that you compile directly from something like Git or are checked into source control, or you can actually override the versions of things that are in Stackage. So as an example of that, we depend on one of the snapshots, but we need a newer version of ASIN, which is JSON encoding and decoding library. So we can still specify, like, I want everything in this version of Stackage, but this newer version of ASIN. And it just works, which has been really great. Changing versions of GHC is really easy too. So here I just changed the version of Stackage, which includes a specific version of GHC. So I think this went from 7.8.4 to 7.10. So LTS 2.2 to 3.15. And it takes care of making sure that it's not using any artifacts that were built with the other version of GHC. So this also includes the ability to check to see if your project will compile with different versions of GHC and really quickly switch between them without even having to like clean everything. With a lot of build tools, I'm kind of paranoid and all, like, if I ever change any sort of build configuration, I'm like, shit, I better clean this to make sure that, you know, it doesn't just work this time, and then the next time I try and build it from scratch, it fails to work. We also have really quick incremental recompile time. So if you've ever used GHCI and used the reload feature, you've seen that when you actually just interpret Haskell code and are basically just doing type checking, recompiling a project incrementally is actually really quick. So here's an example. The resolution's pretty bad here, but I'm just changing the text on a web server and then reloading the page. And you can see that as soon as I save the file and then reload the page, I'm able to see the new text there. It's pretty grainy, but the point being, we don't necessarily have to associate Haskell with this like really slow kind of develop, compile, reload cycle. We can have something that's much more akin to like a Ruby process where you're sort of expecting that you're going to change your code and then just go hit reload in the web server and see the latest changes. There's a couple different ways of doing this. Happy to kind of talk more in detail about this. This is using a project that I wrote called Ordeal. And basically all it does is just kind of automate the process of running your app inside of GHCI, which is the Haskell REPL, running some like main function. In this case, that was a web server, hitting Control-C, typing :reload, which will reload all of the files that have changed, do type checking on them, and then running that web server again. There's another tool that does something very similar just for compilation and build errors called GHCID. So if you've not used that before, I highly recommend checking out GHCID. It's a lot easier to set up than things like HDev tools and GHCmod. It's also 5 times faster than those. You can just like run it in a separate window. I can show people at the end how that looks. Building is easy. What's really cool, because Haskell is a statically compiled language, we can build binaries that, aside from a few C libraries, which will be dynamically linked, the whole thing is just going to be like a single executable that we can SCP onto another machine. We don't have to worry about what version of Ruby is on this other machine, or is the correct version of Gem and all of the dependencies we have installed. We just SCP a binary onto a machine that we want to run it on that's just assumed to be running the same architecture. So that means that deploying is really easy. So it takes some sketch of a basic web app. We have some assets, a favicon, some JavaScript style sheets, and then our statically compiled app. Just by typing stack build, you get this, so you're done. And all we do is make a tarball of this. So we're going to create a tarball. We'll give it a version that includes the git SHA there. Download it from S3 or use SCP or something like that onto the machine. We're going to create a link into current, which is going to be the version of the app that we run now, and then restart the app. And what's cool about this is we actually keep around the old versions of the app. So if we see in production or a staging environment that we're having issues, it's really easy to roll back. All we do is just update this symbolic link to point to the version of the app that we were running before. So we'll keep like 10 versions of the app or whatever on our boxes. They're like 30 megabytes or something, so it doesn't really matter. And if there's ever an issue, it takes like 1 second to roll everything back, which is really cool. These can even be like, this doesn't matter if we're advancing to a new version of GHC, because the GHC runtime is statically linked into your app. You can even roll between different versions of your app compiled with different compiler options, different versions of GHC and stuff. So this is, really, really simple. So that's an example of rolling back to an old SHA. Typically speaking, for our web servers, even under pretty heavy load, we use about 60 megabytes of RAM. When our ops guy first was provisioning machines, sort of expecting more of like a Rails type workload, he was expecting this to be like 600. So that's pretty nice. It's easy to scale to multiple cores. Yeah.
What does heavy load mean? In terms of like requests per second?
Yeah. Tens of thousands. Yeah. It very much depends on what you're actually doing. Certainly if you're just like responding, ping pong, Haskell web servers can do insane throughput. Using pretty much any off-the-shelf Haskell web server, you'll be able to utilize all of your CPUs. So I don't really know too much about the audience in terms of how much Haskell experience you guys have, so feel free to sort of advance me along or ask for more detail. But GHC is going to create a thread per core on your machine and then multiplex lightweight threads onto all of those cores. So if you have 128 concurrent TCP connections on your machine, each of those connections are going to get some roughly fair share of the, in this case, 8 CPUs that I have available. And so even for something like a typical web application, we're able to utilize all of our cores without really doing anything except adding a single GHC compile time option, which might even be the default nowadays. But point being, it's really easy to just basically for free take advantage of all your cores, even for something as simple as a web application. Monitoring is pretty much the same as you'd expect for any other type of app. There's a Java library called Metrics, which is pretty popular with people who do Java stuff, and it basically just exposes a bunch of JVM and user-level application information, things like counters, gauges, different statistics as JSON data. So you have a web server which is listening on a separate port, and then your monitoring tools will just pull those endpoints once every 5 seconds, once a minute, and say, hey, what's the latest JSON data? And then you'll feed that into whatever other monitoring tool you're using, Circonus, Datadog, whatever. So we use a tool called EKG, which is very similar to Metrics, but for Haskell. So it's just going to launch another little web server that's going to listen on port 5000 or whatever, just on the loopback interface. And then our monitoring tools can then talk to this and phone home to Circonus so that we can see all of our statistics for our running apps in one place. It also gives you this little handy web page so that you can actually see charts in real time of these things. So this is showing residency and allocation rate in real time. So you get all these kind of things for free, but you can also create your own statistics that you can register. So you can have something like, how many people are logged onto my site now? So when someone opens a TCP connection, you increment this counter, and when the TCP connection closes, you decrement it. So you can track stuff like that over time. Logging is pretty simple and basically the same thing you do in any other language. So choose whatever logging system your sort of team or ops team wants, logging to a file, standard out, syslog, whatever. And for the most part, this is the same as it would be in any other language. Testing, as I'm sure some of you know, is really fun, and you get a lot of bang for your buck in Haskell with testing. Has anyone heard of QuickCheck before? I assume quite a few people. Yeah. So this is just like a quick introduction to what QuickCheck does, and then I think a fun, pretty illustrative bug that we found. So you basically just write some property about your code. Instead of writing individual unit tests, you say, for any valid input of this type, I expect these things to be true. So I'm going to produce some Boolean value. If this is ever false, that means that the test has failed. And then you let QuickCheck run as many random tests as you want. And because it's the computer, it sort of never forgets to test things like 0, -1, the empty list. And as you build these things up, you can have hundreds of thousands of tests that test these really interesting conditions for larger properties. So an example property, we're going to check that encoding something into JSON. So we're going to say for any event, if we encode it into JSON and then we decode it back, it should be equal to the original thing. So basically it says like, well, we can round trip through JSON with any event type and not lose anything. And it turns out that this failed. So I have some generator, which will generate random events. This is just some algebraic data type that I've created. And I've given it both an ASON instance and a QuickCheck arbitrary instance, so I can generate random ones of these. You see, like, this is literally one line of code to write this test, and I can have 100,000 tests from this now. Anyone have an idea why this would fail? So it turns out that at least at the version of ASON that we were using, it was truncating the resolution of milliseconds that we had. And so I'd have something with a certain millisecond resolution in Haskell, turn it into JSON, the resolution would be dropped, I read it back, and now I no longer have the same resolution. Now, that's not necessarily something that you care about. So you might update your test, but at the very least I know now, I can't necessarily assume that I can serialize a UTC date to JSON and then expect to get the exact same thing back. This is nothing really to do with specifically the test I was writing either. Like I was just saying for any event, and I've now found what's either a bug or an interesting thing with data.time.utc and ASON and this like really interesting interaction now. So wherever possible, we write all of our tests like this because we get to write these really high level, what I think are relatively simple tests, but still find bugs that are like really specific thing in some subtype that we're using. Yeah, so here's an example of, so we've lost that 6 there. Doesn't show up here. I think this has actually changed in ASON recently, but at least the version when I ran this test, this was an issue. As I said before, developing code in Haskell is really fun, and I think can kind of change your expectation of the type of things you can express and the safety that you have. So I'm going to talk about a open source library that we created called PostCritical Transactional that I think kind of illustrates how using Haskell and types can change what you expect to be able to accomplish. Yeah, Luke.
Yeah, do you do anything special for testing I/O? Or benchmarking for that matter?
Yeah, so we use Criterion for benchmarking, which is just like an awesome benchmarking library.
Do you track historical changes with Criterion?
We don't, but I'm really interested in that. I think,
That exists.
yeah,
What
yeah.
do you do for our I/O tests then?
So we use QuickCheck for some of those. In QuickCheck, there's a QuickCheck.monadic.io or something module that allows you to write properties that, like, in the property where you've actually received the random data, you can be an I/O and like return, basically I/O bool. So yeah, we still use QuickCheck for some of that. We have some integration tests that are more akin to like,
Databases?
yeah, traditional stuff. But But I mean, at least my personal philosophy, I'd much rather have that stuff be written with quick check.
So you default to quick check, and then do you use like a test framework or anything, like test framework or?
We use Tasty. Yeah.
And then when do you dump out to like HEMA or something like that, or do you?
We don't. So we just we use buildbot, which is a Python build server for our test stuff, and it basically just shows you like the textual output of each of your build steps, and then looks at the exit code of that step to see whether the test passes or fails, or like that build step passes or fails.
So you write all of your tests as property tests. You have no HEMA tests at all.
We do have a few for some integration type stuff. That's mostly because in that particular case, it was kind of easier to get something working just as kind of an example-based test. But my personal philosophy anyway is like, if I had a little more time, I would write it as a quick check test. There's a few interesting things with quick check, especially for kind of integration tests. You have to sort of figure out, okay, I only want this to run for, let's say a minute, and I have to figure out how many random tests is that. Like, okay, let's say it's 5, but depending on the randomly generated data, it could be 90 seconds or something. So it's certainly not a panacea in that sense. And some other quick check libraries actually let you say, like, test for 3 minutes as opposed to test this number of iterations. Unfortunately, Haskell being the original quick check doesn't necessarily mean it's the most advanced at this point. So there's a few things that I wish were in Haskell quick check that are in some other ones. And then, yeah, I did Erlang for a while and used that one. That one, unfortunately, is not open source, so you have to pay for that one. That being said, quick check in Haskell is still awesome, and I think you'll find at least 50% of tests in the Haskell ecosystem are written with quick check. I don't know, maybe more. Yeah.
Thanks.
Okay, so when we use a relational database like Postgres, typically speaking, we care about transactions. This is like one of the big things that we get from a relational database as opposed to MongoDB or React or something like that. And ideally, we can kind of have transactions that compose together. So, we as Haskellers like to be able to create these like little reusable components that we can compose together, and then they have the same type as the original thing. So we'll kind of talk through an example, see how doing something kind of the naive way has a little bit of an issue, and then see how just a really simple application of types can solve this problem in a way that I've not seen solved with any dynamically typed language anyway. So let's say that we have some query that we're going to write a little function for called lookup_user. It's going to take an email address, and it's going to return the first row that matches this email address and return these appropriate columns. So this will return maybe user or something like that. There may or may not be a user with this email address, and we only expect there to be one. So if there's more than one result, we're just going to ignore the rest of them. That's what this query first is going to do. And so just for ease of naming, let's say we call that foo. That's like one little kind of reusable component that we have here. We want to be able to construct some other ones that can be used independently, bar and baz. And then we might want to actually compose these 3 things together and call it cuz, and say like these 3 things, foo, bar, and baz, all need to be done atomically in a single transaction, right? So the correctness of this greater function cuz is dependent on saying that its constituent parts are run inside of a transaction. And then we later write some function buzz, and then we want to sort of compose cuz and buzz and defizz. And so now we have this kind of like mega transaction, which first should run foo, bar, baz, and then buzz, all in serial inside of a single transaction. And so it seems like everything is well and good, but actually what happens if we sort of do this naively, if we sort of explicitly use transactions inside of here and inside of here. So we say like start transaction, end transaction, start transaction, end transaction, is we end up sending something like this to Postgres. So we actually begin twice, and then we commit twice. Any idea what the problem is there? So let's kind of think through what happens. So first we send begin to Postgres, then we send begin again, and Postgres says, I'm already inside of a transaction, I'm just going to ignore this. And it'll actually send you back a warning saying, you've already started a transaction, you can't start another transaction. So Postgres does not support nested transactions at all. So we've just ignored that second begin, and then we call commit again. Oh, so now we've actually committed in the middle of what we thought was our bigger transaction, and then we ignore the second commit. So now our transaction boundary is actually from here to here, instead of being here to here. And this all type checks fine, but now we actually have a situation where we thought that we had composed all these things into a single large transaction, and if we're not actually looking at what Postgres is telling me, we don't really realize that only part of what we thought we'd kind of composed together is running in a transaction. And you'll see a warning like this. There is already a transaction in progress, and then there is no transaction in progress. And it took me like a month to even kind of decide, I'm going to actually like look and see what's happening here. Because that's the kind of thing, it's just a warning. It's not really an error. And so we have a couple of, this is showing that we're starting the transaction from fizz and then ending the transaction from Cuz's notion of ending the transaction. And so we have a couple of choices. One, we can sort of say that we're not going to explicitly use transactions, and you have to sort of know that whatever function you write is going to be like not composable anymore. If you're like the top of the stack and you're gonna call start transaction, this thing is no longer reusable by another transaction now. And then like in the comment in Cuz, you have to say something like, if you ever call this thing, like make sure you call start transaction. And this is the point that I feel like in a lot of languages, we would sort of just accept this. You know, you have to have some culture of comments or something like that where you sort of agree, hey, you have to be really careful here, make sure that whatever your outer sort of call stack where you talk to Postgres, that's the only place that you call start and end transaction. Or we decide that like Cuz is so important to be wrapped in a transaction that you just can't compose it with anything else. Or if you do, you'll get this weird situation where you thought you had a bigger transaction, but you actually don't. But let's kind of look at what the naive types we were using was and see if we can do better. So you might imagine, and if you're using something like PostgreSQL Simple, which is a popular Postgres driver in Haskell, your type looks something like this. So you take in a connection, you take in the email address as text, and then you return IO maybe user. So right away, we're going to sort of perform this IO action. We have our other kind of reusable reusable query components that we want to compose together. So we want to be able to create a user, create an organization, and then put that user in the organization, and then compose that together all to happen atomically. So we can explicitly call with transaction, and then call each of these subcomponents. Now we've sort of chosen that this is the transactional boundary. Sadly, nothing in the type reflects the fact that we're calling a transaction here. So we could actually compose this with another transaction and have that same problem where we actually have two transactions. Or we can, use comments and say something like, you must wrap this in a transaction when you're ready to kind of finally execute the big thing. So here's where we're composing create user and organization with something else. And now we're calling with transaction around here. So you can see how we can kind of quickly get into a situation where we either accidentally don't put something in a transaction because the implementer wants you to be able to compose this in a bigger transaction. So they just have a comment that says like, hey, be careful to wrap this in a transaction. Or we have a case like this where we think we're doing the right thing in wrapping this in a transaction, but actually because this statement calls with transaction, this whole thing's not in a transaction. We call it begin here, but then we actually commit inside of here, and then this is actually run outside of the transaction. So it turns out there's a really simple solution with types that completely solves the problem. So these were our, this was the type before, and it turns out if we just change this, we're going to create this new PG transaction type, which is basically just a new type wrapper around reader T. So it turns out we can actually just elide the connection. So lookup user, now instead of running in I/O, it's going to run inside of this new type, which we call a PG transaction. And then we'll provide a single function that allows you to turn a PG transaction value into an I/O action. There's no other way to actually get an I/O value out of a PG transaction other than calling this one function. And once you do that, you no longer have the same PG transaction. So what you do is you create all of these little helper functions, and each of them are actually going to run in PG transaction instead. And you compose these things together to get some bigger PG transaction of A. And then the only way to actually turn this into an I/O value, which basically just means like actually execute it against Postgres, is calling run PG transaction. And once you do that, there's no more claim that you can compose this with other transactions. This is like saying I'm ready to actually execute this. So we can use the types to sort of make us decide the level in our program that we actually want to execute this thing. And then we can create these reusable query components that anyone in our application can compose together and make sure that the whole thing composed together runs inside of exactly one transaction. We also get another kind of interesting side effect from this, which is that we can prevent ourselves from shooting ourselves in the foot. Typically speaking, when you're running a database transaction, you want to sort of have, on your end of it, things work as fast as possible. Using a transaction in a database uses database resources. And so if I say start transaction, I do a few queries, and then I just sit there for 15 minutes, the database is actually using resources on the database side to keep that transaction up there. It's keeping an isolated view of the database that is going to be the same as long as you have that transaction open, even though other concurrent users might be editing that same table. So it's keeping this like special view of the table for you, which takes resources on the database side. So it might be that we want to not allow ourselves to do any kind of I/O other than talking to Postgres inside of a transaction. We don't want to accidentally sleep for a few seconds or make an HTTP request. And as much as you can kind of think like, oh, well, I just won't do those things, when you have a project with multiple people and you kind of have these things that can compose together, it's easy to accidentally not realize that you're in a transaction, make some HTTP request that takes 5 minutes, and use resources on the server side. And so it's really easy to prevent this because this slow side effecting thing has a totally different type. We're in PG transaction now, and we're trying to do an I/O action. This just doesn't type check. So now if we want to, we can use the type checker to prevent this whole class of database misuse. If we do want to allow ourselves to do I/O actions inside of a transaction, then we can just make PG transaction an instance of monad I/O, and then we can do lift I/O, some slow side effecting thing. But we have choice here. And so if there's a particular part of our code base where we want to kind of be able to create this description of something which will eventually turn into an I/O action, but not allow other arbitrary I/O actions inside of it, we can use the type system to help us do that. So all of that is an open source library that we have It's built on PostgreSQL Simple, so it basically just exposes the same query, transact, execute mini type functions that PostgreSQL Simple does, but instead of running directly in I/O, it runs in PG transaction so that you can compose these things and make sure that when you're ready to actually execute this statement, that it runs in exactly one transaction.
Can I make one comment?
Yeah.
This is the technique that Reid uses for PostgreSQL Transactional is exactly the same technique that's used in software transactional memory, if you're familiar with that in Haskell. It's exactly verbatim the same exact technique for doing memory transactions.
Yeah, and I think
Anyways.
just sort of building on that, I think that's one of the reasons that STM and Haskell has been as successful as it has, is you can actually create these reusable transaction components that other people can build on. So if you've used the async library in Haskell, it actually exports a bunch of transactions that you can build and compose with your own transactions, and then execute that whole thing as a single STM statement. You know, compare that with like imperative locking. There's no such thing as composing locks together. And even if, you know, there were, it's something very much that you have to be careful about and can't really export to other users as this reusable thing. Anyway, so I would be remiss to talk about all of these great things without also touching on some of the challenges. It's hardly been perfect. One of the biggest things for me, especially early on, luckily this is improved a lot. I've been using Haskell for like 6 or 7 years now, but mostly in kind of an amateur capacity. And there were a lot of things that, you know, were kind of more advanced techniques that were new to me. And there were a few situations where I was building something and like, okay, I'm having trouble getting the types to line up. And you kind of have this like wave of fear of like, am I going to be able to figure this out? In most languages, there's enough escape hatches that you're like, this isn't going to be pretty, but I can do something that will make this work. You know, monkey patching in Ruby or whatever. And so there are escape hatches in Haskell. You have to learn them. They're not, you know, as obvious in other languages, but it can be a little scary the first time that you kind of have some problem that you're like, I don't know how to represent this with types. And I'm afraid that sort of just takes experience and being willing to, you know, ask for help from the community or from coworkers. And then debugging can be interesting. Luckily, there's a lot less bugs in Haskell, so we don't have to worry about this quite as much. But by and large, there's not like a traditional sort of step-through debugger in Haskell. There sort of is if you're using things in G8CI, but there's not really this sort of typical imperative programming notion of breakpoints where you can sort of turn breakpoints on in your program, run it with something like a production load, and then like pop into GDB, inspect the stack, look at things, sort of advance through function by function. I think there's probably a couple of reasons for that. One is laziness. The stack means something pretty different in Haskell than it does in most imperative languages. I think it's also kind of a cultural thing. I think there's no reason that the debugging tooling couldn't be better. And I think in G8C8, there have been some improvements to that. But, you know, be prepared for debugging being different than you're used to, which takes some time to get used to. In exchange for that, there's great profiling tools. I mentioned Criterion before, which is a benchmarking tool, which is just like unmatched for doing micro benchmark type things. So seeing how fast an STM transaction takes in nanoseconds. So not measuring something that takes 15 seconds, but like, how can I get this thing from taking 20 nanoseconds down to 10 nanoseconds and actually have that be reproducible, which is is really cool. I think that's about all I have. I'm around for a bit, so feel free to ask questions. The slides are up on my website. All the open source stuff that I talked about is either on my GitHub or on the Helium GitHub. Yeah, thanks for coming.
Have you looked at Opal?
I have, yeah.
Are there similarities between that and what you're doing?
Yeah, so the question is about Opal, which is it's like a SQL DSL specifically targeting Postgres, but instead of actually writing raw SQL statements, you write Haskell, which then compiles down to a SQL query, which is cool for a couple different reasons. The big one is that it's all completely type safe. So you're sort of making sure that whatever you represent and talk to SQL can actually be read back, and that you're selecting the correct columns. But it also means that when you do things like joins, that you're actually joining on the columns that you think you are, that those columns have matching types. So right now, we're just writing SQL by hand. There's a couple reasons that we haven't switched to Opal. I'll start by saying I would eventually like to switch to something like it, especially because using SQL is kind of like bridging from Haskell, which is this like very statically typed thing, to having like an inline string, which is then going to be sent to a server that's executed. You don't really know whether it's going to fail or succeed until you actually execute it. So probably like at least 50% of the bugs we've had have been in our SQL statements. They're typically things that we find really quickly during development, like, oh, I selected the wrong number of columns. I've added some field to this data type and written a migration, so now I need to like select the user's phone number or something. Most of those are pretty easy to catch, so it's not been that big a deal. The problem with Opal, the last I looked at it, was that it's kind of a lot to bite off. There was quite a bit of boilerplate that you had to do for representing your domain in several places. So like representing your domain as you insert it into the database, which might be different than as you read it, because you might have a serial instance for one of your columns that's incrementing IDs. And so when you insert a user, you don't have to provide an ID, but when you read the user, you do get an ID. And so a user in inserting is not quite the same as a user when reading. And then I don't have enough information yet to know about how good the queries it compiles are. So if you look at the compiled SQL queries, it's sort of like looking at a JavaScript transpiler, right? You sort of have to be willing to look at SQL that looks like it was generated by a machine, not a human, which has potential performance implications, but also potential readability information. So like if I'm looking at the Postgres slow query log and I see, okay, this query is taking 3 seconds, I now have to like take this machine-generated SQL code and map it to Opal Haskell code and figure out which part of my Haskell code base generated this thing. It's like having a bunch of SAS files on your hard drive saying which SAS file produced this CSS or something like that. So I'm not quite been convinced yet to take the effort, but I think it's really cool. Yeah. Matt, yeah.
I've used Opal quite a bit. If you want to talk about it afterwards,
yeah, it's.
I can talk about it. And also, I wrote the exact same thing as PostgreSQL Transactional, only for Opal. I'm the author of that.
It's also possible that Opal stuff has changed a lot since the last I looked at it. So
all of what you said is currently true.
Okay. I really want to use it. So yeah. Anyone else? Yeah.
Like operations for deploys, you said you just execute the binary. You don't do. You just have like a static number of servers that you just don't.
So we're actually, yeah. So we're using Chef, and we download those executables from S3.
Gotcha.
So we have like stored in Chef server. We're like, this is the current version of the app for the development environment, the production environment, the staging environment. And then every time Chef runs, it says, you know, I'm running this SHA. The SHA I'm supposed to be running is this one. If it's different, I got to go download this one, unpack the tarball. Right. I mean, we just wrote like a little shell script that does that. But, I mean, there's a ton of flexibility. Because it's so simple, it means that there's a bunch of different ways you can solve this. As long as you can get the executable on the machine, that's all you have to do, basically. Right. Yeah.
What did you say you use for monitoring?
It's called EKG. Yeah.
Where do you put as the kind of front end to that? Do you plug that into StatsD and all that, or do you use something else?
So we're using Circonus, which is a paid and hosted monitoring solution.
You just export. You don't even go through StatsD for any of that.
Correct. Yeah.
Some monitor your logs too. You have like a log aggregator for centralized logging.
Yeah, so we're using syslog for that. So we have like a central syslog server that all syslogs go to, and then we use Graylog, which is an open source like log viewing system that allows you to, you know, do fuzzy searching and stuff like that. I mean, all of this is stuff that is not Haskell specific at all, which I think is good. I mean, it means that whatever your team or organization wants to do isn't going to have to change because of Haskell.
Yeah, exactly. It doesn't seem like it's anything
Right.
out of the ordinary. Okay. No, that helps.
How many people are running Haskell in production now? Here. A few? All right, cool. How many want to? All right. This is the correct audience. I don't know, has this been like surprising for people? Is it what you expected? Easier, harder?
It seems easier.
I think it's good to see that Haskell can be used for something that's not academic.
Yeah.
So there's that stigma that it's an academic language.
Yeah. Yeah, I mean, I think the main thing I want to show is that for the most part, running it in production is really not different than other languages. There's no special skill set that the rest of your organization has to have if you start, you know, writing Haskell. You just give them a binary. You don't have to sort of change everything in your organization. It's not, you know, as scary as you might imagine.
Yeah, coming in here, like my questions were like, how do you automate builds? How do you automate deploys? How do you do maybe some kind of like checking during builds, like tests or?
Yeah.
How do you monitor do logs?
Right.
Typical operations.
Yeah. So for building stuff, I mean, we do the same thing for all the languages we write. We have a decent amount of C stuff as well for firmware, drivers, stuff like that on our actual embedded devices, and then Lua. So all that stuff is running in buildbot, which is an open source, you know, very similar to Jenkins or something like that. So we just have like a Git commit hook that every time we push something onto GitHub, we build every single SHA. We also use a tool called Bors, which is used to build Rust and Servo, which is really cool. So typically when you do builds, you build the version that you've pushed up, you do some code review. If it passes code review, then you merge it into your master branch, right? But nothing's checking to make sure that that merge commit actually passes tests. And it turns out that when you merge code together, that can either break the build or make test pass. So what Bors does is it checks the SHA that you've pushed up on your pull request or whatever, make sure that builds. Once it's gone through code review, it's going to actually, in a temporary branch, merge your integration branch with master, test that, and then only if that passes and master hasn't changed, it'll fast forward master to be this new merge commit. So it ensures that even if you have like people working on different features and merging stuff in, that master is always buildable and always passes tests. Because Right.
But broken goes on faster.
Yeah, which is just like a waste of everyone's time.
Suppose your database password changes, do you have to recompile?
No, all that stuff is read from config files, which is like stored in encrypted data bags in Chef. Yeah, so we use configurator, which is an open source library to read config files, but there's a bunch of different things. You know, you can read from YAML files or whatever. You can use environment variables. You can use parameters passed on the command line. I mean, this is all basically the same as it would be in other languages. So anything that we would like to change without having to recompile is going to be like a runtime option. And then there's a few C libraries which will be dynamically linked. So like OpenSSL is dynamically linked. So, you know, tomorrow when there's another 0-day OpenSSL issue, we don't have to even change the Haskell code on the machines. We just update OpenSSL on every single one of our boxes and then restart the individual services that are dynamically linking with OpenSSL. Yeah, right. In theory, you could statically link that stuff, though, if you wanted to. Yeah, we're using Nginx. So we have Nginx on each of like the web boxes, and then HA proxy to do load balancing between physical machines. Again, like the same thing you do in pretty much every other type of web app. Or if you have different decisions about how you want to do that, you know, Haskell doesn't make any sort of decision about that for you. Has everyone seen G8CID before? If you haven't, you should see how easy it is to compile. I think I'm going to have to stop the recording here, Jeremy, for this part. How's that size? You guys still read that all right? So G8CID basically just wraps something that will get you at a REPL. So G8CID and then stack G8CI or G8CID Cabal REPL. So it's going to, that was 153 modules. So this is a pretty decent sized project. And then I can take our user object and I'm going to put some compile error in there. The Vim integration makes this really weird sound every time it recompiles with G8CMod. I have no idea why. But you see how quickly that updates there. I think that should disable it. This is cool because especially if you make a change to a module which is imported by a bunch of other modules, if I were to go do like to make that change and then now do stack build, this is, I didn't say that.
Is that annoying?
Right, that was actually pretty fast. Let's change something that's imported by more things.
Cause a type error, don't make a parse error.
All right, yeah.
That's too fast.
So we'll fix. Alright, so that's how fast I don't know how it's been on the whole time?
It's probably HDMI.
Okay. Oh, that's annoying. All right, so now we can see, first it has to build the sub-project here. This is much more like the compile speed of Haskell that you're probably used to, like 4 to 20 seconds for a relatively big project. So this is all of our code in a single stack project, split into a bunch of different Cabal files. But this is like 20,000 lines of code, so it's not too surprising that it takes a while to compile. Can I disable sound or something?
Is that all 6 services in one Git repo then?
It is, yeah. Let's try that. Okay, all right. So you can see that in GHCID there, which I'm just running in like a separate tmux window. Every time I make these changes, it reloads within a few seconds. And that's probably like one of the modules that's imported by other things in our project the most. I still also have GHCID, or GHC mod in here, but you can see how GHCID goes way faster. In a few seconds, GHC mod's going to say there was an error there. I still like to have both because I can do things like ask for the type of things. So I can ask for what the type of what this thing under my cursor is. It takes a while, but it says that's a user, which is cool because Haskell has such good type inference, you don't explicitly annotate types a lot. So if I have like some expression that I want to find out what the type is, I can kind of I can ask GHC mod. So we'll ask what this is. Let's say I don't know what that lens operator is, and then if I type the same thing again, I can like expand the expression that I asked what the type is, which is pretty cool. I think that's, yeah.
Is there like Vim or Emacs integrations for GHCID? Like I haven't used GHCID yet.
Yeah, no, and I think that's kind of the point, is that all it basically depends on is getting to some Haskell REPL. So it doesn't even compare. It doesn't even care if you use Stack or Cabal or whatever.
Well, it wouldn't, because it's doing interpretation, right?
Right.
Yeah.
I mean, it's literally launching a REPL as a subprocess and then communicating it via a pipe, right? But that's good because sadly, the Emacs and VI integration for things like HDev tools and GHC mod break all the time.
Yeah.
They also typically, like, you'll have to use a version of GHC mod compiled with the same version of Haskell that you're trying to check, because it uses HS source extensions or whatever, whereas GHCID doesn't care. It's just a binary that's on your machine that's talking to GHCI on your behalf. Cool. All right. Well, feel free to come up afterward and ask more questions or whatever.
So I just want to give you, there's a lot of new people here today. We've grown hugely since we had the not so brilliant idea to finally get on to Meetup. So I just want to give background because a lot of new faces here. The Chicago Haskell user group's actually been around a long time, I think 2009 or something like that. We've, 2008. So we've been around a long time. Met a few times a year, but we got real serious this year, got a Meetup, and we're trying to do now meet once a month. And right now, with the way we're thinking of structuring this, is we do a presentation 1 month, and then the next month we'll do an informal, like, hacking and just social session. I think there was a lot more socializing than actual hacking last time, which is fine. So next month will be something informal, just to get together. We can come talk to other people about whatever. You can try to if you have questions about Haskell stuff you don't understand, there's a bunch of people who have a lot of experience. They're happy to answer questions. But yeah, we definitely would love to hear any feedback you have about what you would like to see, because now we've got all these new people on here. We've probably got a whole bunch of new ideas and different expert levels. And so what things you want to see presentations about, or things you'd like to see us do differently or better, or we definitely love to hear that. You can contact us through the meetup page. And if you got here some way other than the meetup page, then definitely go check out the meetup page and sign up. Does anybody have any questions?
Also, if you want to present an idea or something, get in contact with us as well.
Yeah.
We're always looking for new talks.
Yeah, we're looking, if you either have an idea for a talk that you would like somebody to give because you don't know anything about it, but you really wish somebody who did would talk about it, we'd love to hear that. Or if you have something you really want to talk about, we're happy to hear what you'd like to talk about. Also, a big thanks to Pivotal for hosting us and supplying all the food. They've been really gracious hosts, and we love coming here. One of these meetups soon will still be in this building, but Pivotal's actually moving. So next time you come, definitely check the invite and see if the location has changed yet. I think it's just up a story, but definitely. Okay, so eventually this location will move, so just keep your eye on the location. We'll probably make a big stink about it too to let people know. But other than that, feel free to socialize and stick around for a little bit and enjoy the remainder of the food. And thank you all for coming out.
Thank you.